So chapter 14, it's an introduction to fluid flow, fluid dynamics, fluid mechanics, and that kind of stuff. Everybody hear me okay? I'm projecting my voice well enough? I was just at a conference in Disney World. Disney World is filled with little children. Little children just carry germs. That's their job. So in case I have something, I'm trying to protect you from that. Okay, so chapter 14, all about fluids, and one of the most important concepts for fluids, to understand how fluids work, is the concept of density. Density is equal to something. What is density equal to? Mass over volume. How much stuff is inside of something divided by how much stuff, how much space that stuff takes up. So if you were to write out the SI units of density, what would the SI units of density be? Kilograms over cubic meters. And we give that a name. What do we call that? Or sorry, that's not the one with the name. We also have pressure. Pressure typically has a capital P. Pressure, it's kind of like mass over volume a little bit. It's force over area. And what are the SI units of that going to be then? Something called Pascal, which is newtons over meters squared. And what is a newton, if we were going to break this down even more? Kilogram meter per second squared over meters squared. So what would we get if we simplified these units? Kilogram per meter second squared, because the meter up top cancels with one of the meters on the bottom. Kilograms over meters times seconds squared are the units of pressure, which we more commonly call Pascal, or Newton over meter squared. Okay. So that's pressure and density. And we can use these things to do useful stuff. One of the most useful things that we use this for is a hydraulic lift, and to lift fluids. And we can do this based on weights of fluids. So the equation that we use for that, and we're going to have to be careful here, lowercase p is equal to p naught plus rho times g times h. This is pressure at some height within a fluid. So where this gets confusing, well, several places. What else is p in physics? P is also how we denote momentum. Here, this is not momentum, this is pressure. So you have to recognize the context of the equation that you're using. So we're repeating the same exact variable, but it means something different here. This is not momentum. Pressure is equal to some reference pressure plus rho times g times h. Rho times g times h is actually pretty much the weight of a fluid. So let's say I have a cup, and I have some liquid in that cup, and I want to calculate what the pressure is at this point inside of the cup, where that red line is. The pressure is equal to a few different things. I've got atmospheric pressure. Atmospheric pressure is just the pressure that's all around us, that's pushing on everything. So there's some atmospheric pressure that's pushing down on all of this. P naught would be pressure of the atmosphere. So that's my reference pressure. But then I also have pressure from the weight of all of that fluid. It's not going to be all of the fluid. It's only the fluid that's above the place where I want the pressure. So that would be this kind of shaded in space right here. So I need to know what the weight of that fluid is, because that weight is pushing down. It's applying a force. And it's applying a force over an area. So the weight of the fluid is going to be the force of that fluid pushing down. Let's do rho times g times h. Where does all of that come from? Well, h. If I were to label h, what do you think h would be? Height. Height. And how would I label that on there? Just in the liquid part. So h is however much liquid you have inside of here. That's where the h comes from. Rho times g. Where does that come from? Rho times G. What is it? Rho is the density of the fluid, which is what? What's density? So it's mass times gravity over volume. What's mass times gravity? What's Fg is mg. So that is the weight of the liquid. That's where all of this comes from. It's the weight of the liquid divided by the volume of the liquid. Okay? That's what rho times G times H comes from. That's however much water. Weight of the water. How many of you have taken chemistry? Did you learn this in your intro chemistry classes? You should have learned this in chemistry. With a guy named Archimedes. You ever heard of Archimedes? You know his story of buoyancy of this? You never heard about Archimedes? Archimedes is awesome. Archimedes, old guy, did some science stuff, and he was working for a king. And the story that I like the best is this king had these crowns that people were bringing him, and he wanted to know which one was the best so that he could reward the people that were giving him good stuff, and he could punish the people that were giving him shit. So he told Archimedes, Archimedes, I need you to figure out a way that I can determine which one of these is actually made of gold and which ones of these are actually fake. Because people were trying to trick him, give him this bling that wasn't actually made of gold. So what Archimedes did is he was trying to think of this, and he had a deadline, he had a timeline, and at the time, timelines weren't like your class timelines where if you submit something late, you just send me a sob story, and I'm like, okay, I'll just take off 1 point and I'll give you credit on it. At the time, if he was late with his assignment, let's kill. Okay, so he's gonna die. Imagine that. Imagine I would kill you if you didn't turn in your stuff on time. How many of you would be dead? Multiple times over. Yeah, me too. Okay, so he had to figure something out, and he was kind of pushing up that deadline, getting right there, and he couldn't figure it out. He's like, oh man, I might as well be clean if I'm going to be killed. So he gets into the bathtub, takes a bath, and he lowers himself into the bath. And what happens when you have a bathtub that's full and you lower yourself into it? Because water level rises. Because of this. Because the weight of whatever you put in the water actually offsets and rises up. So it's buoyancy, Archimedes' principle. And what he realized was, hey, I can take these crowns, and I can take them and I can put them in the water, and depending on how much water they raise, I can figure out which one's the heaviest, so which one's actually made of gold, and which ones aren't. So he was super thrilled about this because he was going to live, so he jumped up out of the bathtub and he ran around the whole kingdom yelling Eureka, including me. Yeah, you've heard that? Yeah? Okay. So, this is where the word Eureka came from, and buoyancy and offsetting water. So it saved Archimedes' life. Really, really helpful. We use this for other things that are really, really helpful still. And that's where the concept of your in-class problem comes from. I'm going to solve that problem for you now. It involves something called the hydraulic press. So we need some terminology. We have a hydraulic system that has an input cylinder and an output cylinder. You assume that the output force is 100 times bigger than the input force, and with that information, what is the ratio of the area of the output cylinder to the input cylinder? This tells you how much useful work you can do with something called a hydraulic press. So a hydraulic press looks something like this. You have some little cylinder over here, and then you fill your system with liquid, and you have another cylinder over here, and you fill this whole thing with liquid. You need a special kind of liquid. You need a liquid that it's called incompressible. Turns out water is a pretty incompressible fluid, and what you can do is you can apply a force onto this input side, so we'll call this F input. So if I push down with some force, and this has some area that goes along with it, so this little piston is some area in. What's going to happen if I push down on this side? What happens to the water? It gets pushed. The water that's in this part gets pushed down. What happens to the water that's in the bottom part? Where does it get pushed? It gets pushed over to the right. So what happens to this water? It gets pushed up. So what happens to this cylinder? It gets pushed up. Okay, so we're applying the force to every single point inside of that liquid. The liquid is incompressible, which means that this liquid doesn't squeeze. Every kind of force that I apply at this point gets applied to the next point. If it was a compressible fluid, what would happen? What? It wouldn't rise as much. So if this is compressible, it's like you had a spring inside of here instead of a bar, and it will kind of squeeze a little bit and lose some of the pressure that you were outputting. Okay, so we're going to take this force, we're going to push down, and we have this area that we're pushing down on, and it's going to give us an output, F out, over the span of this A out. And what we know is if you have an incompressible fluid, then the pressure that you put in is equal to the pressure that you put out. P in equals P out. This all works very nicely in the ideal world. In engineering, you're not always working in the ideal world. In biology, you're not working in the ideal world. So this doesn't actually end up panning out. And the hard part is figuring out where the forces go, where the pressures go. However, we're in intro physics. Do we care about the real world? No, we're just ideal. So pressure in. What's the equation for pressure?
Force over area.
General equation, force over area. So we have a force in divided by an area in. That has to be equal to pressure out. What would pressure out be then? Force out over area out. And in this problem, we are asked, we have a hydraulic system with an input cylinder and an output cylinder. We assume the output force is 100 times bigger than the input force. So if I have some F in, that's equal to, let's say, F in, then F out, what is F out equal to?
100 F in.
100 times F in. And I'm asked to find the ratio of the area of the output cylinder to the input cylinder. So I need to find A out over A in. How do I do that? Can I solve this and get A out over A in on one side? Yeah, so how do I do that?
Multiply A out to the other side.
Multiply A out to the other side, okay. So I have A out over A in times F in equals F out. So my A outs on the right-hand side cancel out. Now what do I need to do? Divide by F in. F in cancels. And I have A out over A in equals F out over F in. Can I plug anything out? Plug anything in? F out is 100 times F in. And what's F in? I just said F in was F in. They cancel out. And A out over A in gives me 100. So that's the ratio of my areas. Yes? Right here? Right here? So for here, what I needed to do, I needed to get A out divided by A in by itself. So I divided both sides by F in. That got rid of F in on the left-hand side and moved it over to the right-hand side. Because the question asks me, what's the ratio of the area out over the area in? So this is exactly what I'm looking for. Yeah. Is that good? Yeah? Yeah, that's good? Yeah. Okay. For the in-class problem, you are doing problem number 60. This is actually problem number 62, but problem number 62 has some troubling wording that they use, unless they've changed it. They might have changed it. Any questions on this? I have an extra challenge question for you too. If you can figure out the answer to this and how to do this, then I'll give you 5 extra points on your next week's exam. This is due by the end of class today. So it involves this system right here. This is called a bioprinter. So if you want to start 3D printing hearts and lungs and ears and tissues and all sorts of stuff, then you use something that's similar to this. The way this works is you take a material that's compatible with the body that you can put into the body, and you load up this big giant syringe with that material. And then you push with a little motor, pushes that material out of this hole. And then you run a little tube that comes through and makes the material come out of this little syringe. And this whole system can draw whatever shape you want. So you can draw little lines, you can draw a little vasculature, you can 3D print organs with this. Right? If you look at this, I've got a cylinder here, and I'm pushing on it. I've got a cylinder here, and I'm pushing on it. It's that. Pressure in equals pressure out. So the pressure that I'm applying here gives me the pressure that I apply out here. What you need to do for this bonus question is you want to figure out, I want to know what's the maximum force that I can apply here and not kill the cells coming out here. Cells. You should have learned this in biology. Cells can withstand certain force. Did you learn about this? Cells can withstand the force before the cell wall breaks. You learned this. Biology, yes. Okay, so what I want you to do is Google and find what force the cell can withstand. That is the maximum force that you can have coming out. Right? I want you to get the maximum force that you can apply in to get that force coming out. What other 2 numbers do you need?
The area.
The area in and the area out. How do I get the area in?
The diameter.
Measuring. How do I get the area out? Measuring. Okay? If you can tell me the force that I can apply in my software to push my cells through for a cell to survive, then you get 5 extra points. So write up the whole solution to that problem and how you did it. If you want to make measurements, which you will need to, there's your printer right there. Okay? That's how we what it is. We'll call that pressure. Any questions on any of this? Okay. I'll go ahead and list up your chapter 15 and 16, make those available to you. I'll get to work on your in-class stuff. I'll come around and answer any questions you might have.